In this video, I'm combining the first lesson in Module 11 with about the first half of the second lesson. Reason being that there's a lot of stuff that they do in the first lesson that, in the interest of time, I'm kind of skimming over because you're not going to be asked to do that on the EOC. It's not something you absolutely must be able to do in order to move on to other math classes. So we're just kind of glancing over a few topics. So a dilation, you see here the definition, is a transformation. So we're talking about transformations again, but notice that it will change the size of the polygon, but it'll leave the shape unchanged. So when we're talking about a dilation, we have a center of its dilation and we have a scale factor. So just as a comparison, remember that when we did reflections, there was a line of reflection. When we did rotations, there was a center of rotation. When we did translations, there was a vector of the translation. So a dilation also has its components. So in this activity that they have in the text, they have this triangle ABC and then A prime, B prime, C prime. And they want you to measure the lengths and they want you to measure the angles. And again, in the interest of time, I'm not going to do that. But what I want you to observe is, okay, so here's pretty much triangle ABC. And if I take it over here, notice that angle A is congruent to angle A prime. Angle B is congruent to angle B prime. And angle C is congruent to angle C prime. But the lengths obviously are not the same. However, if I were to shrink the entire triangle down, it would eventually line up onto triangle A prime, B prime, C prime. Okay, so it's not working perfectly, but you may remember it didn't line up perfectly on A, B, C either. Okay, so what do we notice about the corresponding sides of the figures? What do we notice about the corresponding angles? The corresponding sides are always in the same ratio. Corresponding angles are congruent. And what similarities are there between reflections, translations, rotations, and dilations? All of these transformations preserve angle measure. And all of them, except for dilations, preserve segment length. Here, they're talking about dilating segment AC with O as the center of the dilation, and we're dilating it by a factor of 3. Now, I'm not going to do the full dilation, but understand kind of the concept of it. So the way that it would work is I would draw a ray from O through C, and where C prime would end up is I would use the length of OC, and OC prime would have to be 3 times as long as OC. And I would do the same thing with OB, and I would do the same thing with OA. So as I mentioned before, the lengths of the images would be 3 times the lengths of the pre-image. And again, the reason for that is because I'm dilating it by a scale factor of 3. In this reflect question, it's asking us to make a conjecture about the length of the image if the pre-image is a 4 centimeter segment and it's being dilated with a scale factor of k. Well, what I'd hope that you'd notice is basically the image is always the original length times the scale factor. So the image would equal 4k. The second part of the question is, can the image ever be shorter than the pre-image? And it can be. The image would be shorter if k was less than 1. So for instance, if my scale factor was 1/2, then the image would be half as long as the pre-image. What can we say about the image of a segment under a dilation? Let's come back over here and consider where segment AC would have eventually landed. It would have been approximately something like that. And while my sketch isn't perfect, what I'd hope that you'd kind of notice I'm aiming for is that AC is parallel to A prime C prime. And so the image of a segment is going to be parallel to its pre-image, unless the segment passes through the center of dilation. Then the image would be collinear with the pre-image. So let me illustrate what I mean by that. So if I have a segment and I have, this as my center of dilation, and I'm dilating this segment with a scale factor of 2, then what's going to end up happening is I'll end up with another segment also passing through this point, and it would kind of be like this. So notice that it's collinear. It's on the same line as the pre-image. A couple of properties of dilation. So we've already talked about how a dilation has a center of dilation and a scale factor. We've already talked about how dilations preserve angle measure. They also preserve betweenness, collinearity, orientation. Orientation, remember, is something that is affected by reflections. Remember that when we reflect a figure, we change the orientation. Dilations preserve that orientation. In example 1, here we're determining whether the transformation is a dilation. So a couple, kind of like a checklist they have going on here. Are the angles in A prime, B prime, C prime, D prime congruent to the angles in A, B, C, D? Yes. Is it preserving betweenness? Yes. Is it preserving collinearity? Yes. Is it preserving orientation? No. The ratio of the corresponding sides is 1:1. And is this a dilation? No. It doesn't preserve orientation. This is a reflection. In this example, determine if the transformation is a dilation. So first of all, I would hope that you'd notice that it looks like a reflection more so than a dilation. Also, notice that while AB equals A prime, B prime, the length of BC does not equal B prime, C prime. So this is definitely not a dilation, because if whatever the ratio is between these segments, it should be the same for all of them. So this is not a dilation, and it's not a congruence transformation at all. Here we're talking about similarity transformations. So the concept of taking one figure and mapping it onto another, now using a combination of dilations, rotations, reflections, translations. So in example A, it says trace EFGH and turn the paper so that EFGH is mapped onto patio LMON. And since you would turn the paper so that EFGH would map onto LMON, the description for this transformation would be that it is a rotation of 180 degrees, it looks like. And what does this confirm about the patios? The patios are congruent, because remember that a rotation is a congruence transformation. Part B, it says trace them and fold the paper so that statue ABCDEF is mapped onto statue JKLMNO. Describe the transformation. What does this confirm about the statues? Well, if we're folding the paper, then it should be apparent that it's a reflection, and it's a reflection over the y-axis. And so that means that the two statues are congruent. In part C, describe the transformation that would map triangle RST to DEF. Well, this is definitely not a congruence transformation. These two figures are not congruent. Hopefully, you'd realize that it's definitely a dilation. Well, how would I have to dilate RST in order to get DEF? Well, notice that coordinates of E are 0, 2, whereas S is 0, 4. So 0, 4 mapped onto 0, 2. T is located at 8, -2, and it mapped onto 4, -1. R is at -4, -2, and it mapped to -2, -1. So what I'd hope that you'd notice here is that x, y mapped onto 0.5x and 0.5y. And so what does this confirm about the gardens? This is because this is a dilation, meaning all of the coordinates got multiplied by the same number, the gardens are similar. So looking back at all of these steps, were any of the images congruent to the pre-images? Yes, the ones which were mapped using a congruence transformation, such as a rotation or a reflection. And so what this means is that congruent figures are also similar. In this example, we're trying to determine whether the figures are similar using a similarity transformation. So P is located at 2, 2. Its image is W, located at 5, 5. Q is located at 2, 4. Its image is at X, 5, 9. R is at 6, 4. And its image is Y, located at 12, 9. And Z is at 12, 5. Its pre-image is S, located at 6, 2. So you're probably noticing that there might not be a nice, neat multiplication going on. Let's see. If I multiply my R and S X coordinates by 2, that works out really nicely here, but not for P and Q. Okay, so something else must be going on there. And then for the y coordinates, what you might notice is that the y coordinates are being multiplied by 2, and then I'm adding 1. Okay, so let's find each distance. PQ is 2 units long, QR is 4 units long, WX is 4 units long, and XY is 7 units long. Okay, so if K times PQ equals WX, then my scale factor K would be 2. However, when I try to use that 2 to double QR and find the length of XY, it doesn't work. So that means that there is no value of K that can be determined that would map PQRS to WXYZ, so the figures are not similar. Here, let's find the length of LM. It is 3. The length of OL is 4, compared to GH, which would correspond to LM. GH is 6 units long, and GK is 8 units long. And since visually we can see that these are both rectangles, so that means, is there some value that I can multiply 3 by to get 6 that I would also multiply 4 by in order to get 8? And yes, there is. My scale factor is 2. So yes, LMNO was dilated by a scale factor of 2. In this example, I might consider taking triangle MNP and trying to reflect it so that it looks more like JKL, but then I would hope that you'd realize, JKL actually is isosceles, whereas MP is very clearly shorter than NM, and KL equals NP. So for number 4, no, this is not a similarity transformation. How is the question phrased? Are the figures similar? No, they are not. There is no similarity transformation.